Hello everybody, welcome back to the Gregorius Maths video. Welcome back to the Advent calendar. It's day 4 today. And today I'm going to be making a video on the first isomorphism theorem and why you've actually been using it this whole time, even if you don't realize it. And this is a realization I only came to a few weeks ago when I was doing a problem. And I thought it was a pretty cool realization, which after I say it sounds obvious, but you might not have thought about the first isomorphism theorem in this way. I certainly hadn't, and I'd seen it for years before that, so I thought I would make a video on this, and hopefully you find this cool. So just to begin, the first isomorphism theorem is telling us that if we have some map phi, and the reason I say map is because I could be talking about a linear map if x and y are vector spaces, or I could be talking about homomorphism if x and y are groups. So an appropriate map, let's say, between x and y. In a nutshell, the first isomorphism theorem is telling us that x mod the kernel of phi is isomorphic to the image. So I should say more words there, but in a nutshell, this is what it's saying. This video is not meant to be a precise proof of the first isomorphism theorem or anything. I'm assuming you've seen the statement before, or this is sufficient for you to carry on the video. But basically, this quotient here is isomorphic to the image. Now, what I want to show you is that you've been doing this the whole time. So my first example of this is differential equations. So in differential equations, let's say I want to solve a second order ODE. So let's say I want to solve y double prime plus 7y prime plus 6y equals 0. Oh, sorry, not equals 0, equals f for some f. What's the general approach? The general approach is you solve the homogeneous equation. So you solve y double prime plus 7y prime plus 6y equals 0. This gives you the complementary functions. And then you find the particular solution, which satisfies this equation here. And then you just say that the general solution is y equals the particular solution plus yc. And this is the general solution. So in general, that's how we want to solve this. So we find the complementary functions, and then we find the particular solution, and we add the two together to get the general solution. But I want to tell you now that this is actually just this statement here is just the first isomorphism theorem at work. So say now, consider, okay, some linear operator L, which takes in some smooth function and gives you another smooth function. And what does L do? So this is a linear map between vector spaces, and L of y is equal to this thing. So y double prime plus 6y prime plus 7y prime plus 6y. Now, we want to apply, since this is a linear map, because differentiation is linear, we want to apply the first isomorphism theorem to it. So what's it saying? It's saying that the space of smooth functions modded out by the kernel of phi is isomorphic to the image. Okay, cool. I've just literally just plugged it in, so that's not very helpful. Bear with me. So what are we actually seeing here? Well, the image is the set of all possible right-hand sides of this equation. So the image, say we have L, the image is just the set of all f such that f is equal to L of y, for some y. So if we put this equal to f, then the image is just the set of all right-hand sides. And this quotient here is, well, our input y is just the solution to the differential equation. So if we input so say we input sine into here, and we get sine double prime plus 7 sine prime plus 6 sine x equals some function f, well, by definition, y is the solution to that differential equation. So on the left-hand side here, we have the solutions, but we mod out by the kernel. And what's the kernel consist of? Well, the kernel is just the set of all y such that L of y is equal to 0. But if we have L of y equals 0, that's precisely the complementary functions. And so each element of the image is represented by a coset, because remember this quotient gives us cosets. So each element of the image is represented by a coset, which is a solution, aka yp, the particular solution, plus the complementary function, which is just modding out by the kernel. So in general, we have that some solution to this for some given some right-hand side f, the solutions are given by, in general, y equals to yp, which is the particular solution, but then we mod out by the kernel, so plus the kernel, oh sorry, I'm not saying, I should say L, sorry, I'm using L here, plus the kernel of L, but this is just equal to yp plus the complementary solutions which you get. So this statement here is really just, we're talking about cosets. So this is just, yp is just a representative of the coset. And that's all we're doing. So we're really using, when we do this approach, when we find the elements of the kernel, which is a complementary function, and then we find the particular solution, we're just finding a representative for the coset, and then we just put the first isomorphism theorem to use, and we say, okay, so our general solution must be of this form here. Okay, that's enlightening, I hope. Now, a quick pit stop to something that is slightly more standard, I think, just while we're on vector spaces at the moment. Another use of the first isomorphism theorem is the rank nullity theorem. And this follows pretty much immediately. So if we're given a linear map from V to W, say, then the first isomorphism theorem tells us that V mod the kernel of phi is isomorphic to the image, and yes, is isomorphic to the image. And so what do we have? Well, assuming these are finite vector spaces, if we take the dimensions, then we have that the dimension of V minus the dimension of the kernel is equal to the dimension of the image. Now, the dimension of the kernel is just the nullity, that's just the definition. Dimension of the image is just the rank. Rearrange, you get that the dimension of V is equal to the rank of phi plus the nullity of phi. So you get rank nullity for free as well from the first isomorphism theorem, which is just a quick side note that I wanted to point out. But now, another place where you have been using the first isomorphism theorem that you may not have expected to be using it is in modular arithmetic. So say I wanted to solve the equation 3x plus 2y equals 1, right? So I guess you could use the Chinese remainder theorem. You could do it mod 2, find x mod 2 and find y mod 3, and then use the Chinese remainder theorem and see what you get. But another way you could do this is by Bezout, or the Euclidean algorithm or whatever, you could find a particular solution. In this case, it pops out pretty immediately. X equals 1, y equals minus 1. And then, well, these aren't the only solutions, because if we had x equals 1 plus 2t, and since we are adding 2t here, we need to take away 3t here, and y equals minus 1 minus 3t, we would still have solutions, and these would be the general solutions. So what's happening in general here? well, here we're considering a group homomorphism, phi, which I'll use with the other phi this time, which takes in a pair of integers, x, y, and it outputs 3x plus 2y, like so. So this is a homomorphism which you can easily check. And, well, what do we want to do? Well, we want to find the solution to this equation, right? So, well, what do we have? Well, first things first, we have that okay, let's write this out. So, Z2 mod the kernel of phi is isomorphic to the image, which in this case, because we can get 1, we can get the whole integers, it's isomorphic to the integers. Now, okay, good. So what are we saying here? Well, if we get 1 on this side, again, 1 is in the image. Cool. So that's the solution to this equation. And, sorry, that's the right-hand side of this equation. And then on the left-hand side, we have the pair xy, which is a solution. And so 1 minus 1 is on the left-hand side. But because we're modding out by the kernel, we actually have that the right-hand side is represented by a whole coset because we're modding out by the kernel. And so the right-hand side is not just going to be 1 minus 1. We have to add the kernel. We have to add the coset. Sorry, we have to, because we're in a coset, we get all elements of the form 1 minus 1 plus something in the kernel, right, is equal to xy. Because again, we're working within a coset. So basically, what we're saying is if we're working with a good enough map, then adding stuff in the kernel does nothing, right? This is like a really formal way of saying that, basically. And here we can easily see, okay, if 3x plus 2y equals 0, then x has got to be 2t and y has got to be minus 3t. And so therefore, we get that our solutions are precisely equal to, again, we take a particular solution, 1 minus 1, and then we add the kernel, which is just any integers of the form 2t minus 3t, like so, any pair like that. And indeed, I won't go into it now, but you can actually use the first isomorphism theorem to prove the Chinese remainder theorem. In fact, that might actually be the standard proof. I'm not sure, but yeah. So this generalizes further, basically, is what I'm saying. It generalizes all the way to rings. But yeah, I mean, I hope so. So it appears in differential equations. It appears with rank nullity, and it also appears in modular arithmetic. And these are all fairly elementary examples of stuff that you probably would do before learning the first isomorphism theorem, and yet secretly you were still using it. So hopefully this has given you some extra intuition about the first isomorphism theorem. Hopefully you found this interesting, and if you did, then join me for day 5 of the Advent calendar. See you later.